All right. Hello, everybody, and welcome to this Cloud Lunch and Learn session. My name is Dwayne Netwick, and I am your moderator today. And with me today is Francesco Barali, and he is going to talk about microservices and how and what how to elude, I guess, communication issues and help to avoid them from failing, or at least recover from failing. We'll find out as he talks through it, but. And sounds like fun. A dramatic opera of multiple acts. So we've got some opera today. So we're getting some culture into the session today. So thank you very much, friend Francesco. Feel free to provide any if you have any questions, put them in the chat in YouTube, and we will be able to get them over to Francesco to answer. So with that being said, I will turn it over to you. Have a great session.
Cool. Thank you, Dwayne. Thank you for handing me the mic. And yeah, as introduced today, I'd like to go through with you on a small journey that occurred to me last year when I was working in Ireland for a company. And they actually, in a journey through their marvelous and intricate microservices, let's say, yard. So basically, what I want to talk to you today is really not much about the theory, sorry, about microservices, the architecture, how they communicate between each other and stuff, because there is really plenty of stuff to learn from on the web. But I'd like to show you a practical use case on how in a microservice architecture the communication between each other and their successes or failures comes into play. How usually it's good to react to them, or how do we observe them in order not not for them to fail again, or correct them in a way, or recover manually or not manually. So first of all, I want to talk just briefly about myself. I'm Francesco Borrelli. I'm Italian, as you might guess from my name. I'm 8+ years software engineer in the field, worked in multiple and very diverse projects throughout these years. I'm currently as a senior software engineer in Shutterstock, and I've worked with cloud solutions for like 5 years, 4 years roughly. And in the cloud itself, I proudly founded many side projects and startups that failed in a matter of months. But all these failures and successes gave me enough experience to kind of understand and try to put up all those scars into play when it most mattered. So before talking about microservices, how they behave, how they are made up, and how do we choose what is a microservice or not, we should start from basically where it all started, and I guess where we, as software engineers, developers, or basically IT persons, started from. So here comes into play the monolith. The monolith, just to give you a few sentences around it, it's this huge, or little as it is, but it's scary behemoth of a code base or service, which has basically everything into it. It has all the information and the data we need about the application, all the controllers, so all the business logic basically behind it, all the nits and bits needed for the whole services, which might be a website, or I don't know, even a single service inside clusters of services. And also it also hosts all the interfaces. This kind of architecture is usually referred to as a layer, okay, kind of architecture, because of course you stack different, okay, layers of responsibility on top of one another. But the thing is that in the monolith, you have all the different parts of the application all together, so into one code base usually, and into one service deployed somewhere. It can be quite intuitive to think that uh, this kind of approach leads to some problems. Of course, if you think about it, it can be a monolith. It's not flexible at all. And by flexibility, I mean all of the different modules are really tightly coupled between each other. Okay, and if you want to make a change somewhere, usually it impacts another part of the code somewhere else. So if I change some kind of model, a data model, usually I have to make and adapt these changes like a cascade all down to, I don't know, the business logic or the presentation layer to the different clients. And this can lead to unexpected consequences. It's not really prone to scalability. And by scalability, I mean in the both direction. So it can easily kind of scale up because you can always, put more resources into a single instance or stuff. But, even to that, there is a kind of limit, both hardware and, money wise. But you can also, of course, scale it horizontally, which means if I want to have more horsepower because I have more workers that do some job. But since we are in a monolithic architecture, so it means that everything is into one big space. It means that you can have two, for example, same instance of the same service or the same monolith. Because of course, since the data layer, so for example, the database it is inside of it, it basically happens that you need a way to share the database somehow, and it starts to complicate things. And this lack of modularity also makes it difficult to identify and isolate performance bottlenecks. And also, with this approach, you can't actually identify and try to scale and increase the performance of the different components of this system. Then, of course, the having everything into one space means that all the different modules and components inside of it are really highly coupled, which means that any changes to a module, as we said in the first point, any change from one module can directly impact the behavior of others. So it's, on the long run, it makes it harder to maintain the whole system. And also, on top of that, it becomes challenging to track down the sources of any issues that can arise. And the last thing is that a monolithic architecture, by it's basically or a monolithic project, I say, can lead to a really limited technology stack. It means that you need to be bind to a tech stack of your choice, your programming language, your database, your caching layer if you want, or anything else that can fit into your project. So during the history of software engineering and stuff, we try to have one of the I try to adopt and embrace on one of the most known probably Latin proverb, which is divide et impera. So we tried to divide all these monoliths, big huge applications, into small services. And here comes into play our first actor, let's say the microservices. But actually, what is a microservices? Well, it's like giving a definition of a startup. It's really difficult because everyone can interpret it and have different views of what is a microservices or service. But what I like always to do when I need to find the meaning behind something is to go to the etymology of it and try to understand why it has been called that way. So simply, we are going to this definition, which is micro, which comes from the Greek mikros, which is literally small, and service from Latin service, which is literally means a slave. So actually, microservices can be called small slave or something like that. But if we actually put this definition into our context, we can outline a few characteristic, okay, of a microservice. So what a microservice actually is a autonomous specialized unit of code that's been developed, deployed, and operated and scaled independently. So you can always see difference from the monolithic architecture, because a microservice will actually have its own domain on, or like its own scope on which it operates. And also, the fact that they are autonomous, it means that they can be assigned to different teams. Okay, they can be developed by different teams. They can be then built differently. It doesn't matter if they need to share the same tech stack, or I don't know, same tech choices whatsoever. So this kind of approach can lead to many benefits. But just to take a step further, the first question we, all the every time I had in my mind when starting, for example, a new project or bootstrapping a new team whatsoever, was, should I actually adopt a microservice architecture? Well, the answer to this question is quite let's say complex. So I'd say it depends. It depends because you have to, for before that you need to answer other questions. Okay, you need to take into account a few concepts. So imagine, let's imagine we are starting from a simple application, okay, that's been built as a monolith, and we have it, and we are starting to feel tight and, compressed by this, all in one place kind of um, architecture. So what I usually do from this starting point is try to make most of the monolith that I have, because I'd like, before anything else, I'd like to streamline the development life cycle. If it is difficult and it becomes cumbersome to make changes and add new things onto the code base, I before go and streamline the development life cycle, which means automate a lot of stuff, CI/CD as a priority, automate the tests, and all this kind of stuff. That really helps the let's say the long run maintenance health of a project. Then I also, if I'm working a multi-team company, I'd go to improve the team autonomy. So making different microservices owned by different teams. For example, I'd have an entire CRM team, okay, owning the, for example, I don't know, the product microservice, and another orders microservices. And by owning, I mean taking inside of the team all the responsibilities of keeping up the microservice and developing new features or maintaining it, and observe, making actually a good layer of observability around it. And also, if there's achievable stuff that, especially in, well, old projects and projects that have been running for a long time and are basically kind of, um, the baseline of many other projects, it's not possible to modernize the tech stack, but if it is doable, it should be done before going and adopting a whole microservice architecture. So basically, that's because a monolithic infrastructure is actually cheaper to, in the first at the first glance, it could be cheaper to implement and to maintain, and also cost wise it can be cheaper if you're going on a cloud vendor, or in general, if you are doing on premises kind of infrastructure, it can be cheaper to maintain. And it's also easier if you're bootstrapping on your project. It's easier to bootstrap and develop on a monolith, because all the things are there and you don't need to create any kind of communication or permissions or any magic that needs to happen between different services to make them communicate and or share anything. And the one thing that I also want to make clear is that adopting a microservice architecture means increasing the complexity of the overall project, because one thing, it can increase the latency in some APIs or procedures, and on the other side, it actually increases the complexity of communicating between these services, of maintaining them, and making sure that all of them communicate in the right way, basically, and behaves in the right way. So adopting a microservices is necessary only if you have to do it, because microservices are not a magic wand or pixie dust, as I read on our website. They are not the go-to, the cure-all medicine, and basically we are only moving the complexity, okay, from a space to another. Then we should not adopt a microservice architecture if that's our goal. So if we are doing it only for the sake of it, we should not adopt a microservice architecture because it's cool or it's fun or it's the next new thing. If And then if there is an actual need to that, and it's actually there is this necessary need, okay, for microservices to be there, there is a need to face and embrace, okay, the complexity that comes with it, which means creating, as I say, communication channels, observability for the different microservices, a whole DevOps department that probably needs to spin up containers and other stuff that comes with it. And of course, if since we are adding or moving our, let's say, moving this complexity out to be more, let's say, visible, never let's try not to over-engineer and make the simple the better things before anything else. And that's because we are already adding complexity on the outside. There is no need to put other stuff on top of it. So as much as I love going through rabbit holes, defining, for example, trying to put some definitions and methods on how, for example, should we define a microservices? How then, if you want to adopt a microservice architecture, how do we separate the different modules in the whole monolith to create a correct and domain specific microservices? What are those communication patterns that can be used between them? Or if something fails, which is the main topic of this presentation, how should we react to them? So how do we first of all catch these failures, and how do we react to them? But I don't want to get too much theoretical about this, but I think that real cases are way better for two reasons. First of all, they show good examples on how to do stuff, because if I want to do the good deed, okay, of most of the times I'm just blankly watching, getting my stare at the wall, just because I don't know to practically how to do it. And the second reason is because to actually show that this is possible and this is actually achievable. And there are some compromises and few takeaways from that. So the real case is this. In one of my previous job, I was working for therapy clinic, which is it's a big multinational at this point. Um, uh, let's say chain of beauty clinics. It currently has more than 60 clinics between US, UK, and the Republic of Ireland. And I was working in the newly formed tech team. The whole tech team organization, let's say, was roughly 40 persons, divided into six. At the time when I started this project, it was six teams. And each of them was a streamlined team with 100% ownership on all the services and project that we were taking on, and all of them were really loosely decoupled between each other. And these produce a lot of microservices that then were basically the reflection of the teams. So I was working in particular into this internal tools team, okay, that were that had as a first goal to build a new CRM for the clinics and the operators of those clinics. Well, one of the other goals and topics that was going around between the teams is that we needed to replace the old payment provider, because, of course, it was an old solution. It was a not good fit for our new implementations, and we need to move away from that, basically. So, me, another engineer, and two tech leads form basically a new team around this project, which we call the payment gateway. So we were tasked to design, implement, and create this payment gateway, which is basically a one single point that was needed to support all the payments integration for all the teams. So I don't know, for the e-commerce team, for the CRM team, and also for the data analytics team as well. So we had to support different kind of actions and features for all these use cases. So we sat down and we listed a few, some, let's say, priorities. We needed it, of course, this service of payment gateway of this sort needed to be reliable 100%, because we are talking about money and nobody likes when money get lost. So we needed to focus on being this service being really reliable, and it needs to also be integrated with third-party services. We are moving away from our old payment provider and we adopted Stripe as the new one. And also we needed this payment gateway needed to have tight communication with the other microservices that were being developed and deployed by other teams. You need, of course, to be continuously monitored because we didn't want to lose any trace on any failures or even success. And of course, it needed to be easily extensible in the mean that basically we needed to really we need to extend the payment gateway to support new flows and new transactions, let's say, easily. We didn't want to spend too much time on extending this piece. So let's not second have drawn some box and lines and figure out what was the flow. Okay, so let's say we have our wonderful hairy customer that was getting into a clinic to get a laser hair removal treatment. You enter the clinic, go to the front of house agent. He would ask for it, etc. Once it was going, okay, I have my appointment. Let's say decided, I'm going to pay. Okay, I'll get presented the point of sale, the terminal, the physical one. I get out my phone, tap it, and bam, it would load. All the information go to the CRM, and then basically everything gets hands out to the clouds, to a bunch of magic thing that happen. Then the terminal says, "Oh, wow, congratulations, you have money on your car, perfect, you can have your hair removed, yay. But actually, of course, I for the sake of dramatic entrance, I left the magic hidden for a second, because what's actually happening behind the curtains is this. So when we create, when we had to do a payment, okay, collect a payment, so make a actually payment request, we would first of all collect the money via Stripe to say and tell the system that actually freeze the money on Stripe, to say that the user had the necessary money on the card. Perfect. Then if that's then after that, registering the order, okay, on our CRM external services, which was not maintained or developed by us, was at the point was an external company that was selling to the company, to my company, a service basically to manage some of their backend infrastructure. So it was software that we did not had any influence on in any way. Then, if the order was registered successfully, we would also register the change if any product, for example, was bought, for example, a cream, a lotion, whatsoever, into our internal inventory service. And then, of course, the update would be sent to the CRM and to the terminal, then again to the client, happy client. So it's quite linear flow, like a multi-step. We call that a multi-step transaction because, of course, it's a transaction and it involves different and diverse steps to be completed. And there are a few caveats of this flow. Okay, there are a few let's say there are a few turning points that can be really bad around this flow. For example, first thing is that all of these were independently services. Okay, the Stripe is something that of course we can change, we couldn't change. The external CRM and was another piece was that was externally managed and we couldn't change or adapt or do anything. And the inventory service was something that was, yes, managed and developed internally, but we, of course, we didn't want to make some changes on that, only to support the payment, let's say the payment features. Okay, we wanted to have some integration that in a lean way would introduce and put this feature out in the public. So we noticed that, of course, we are handling different actors at this point. Okay, we are moving actors and communication. We understood that communication was a key part of it. So the complexity was everything, most of it was into the communication itself. So we had a few questions. So how do we actually orchestrate this multi-step transaction? So how do we move this different part? How do we say, okay, you go, you don't, you did good, you did bad, etc. Then if we understand how to manage those different parties, if one of them, trips and fails, basically, what do we do then? How do we react? What's our action? How can even understand the status of the whole flow, the status of the different steps, how we can understand at what point our flow is. And of course, to imagine that has a big and huge drama, our majestic orchestra director comes into play, that we found out after I found out after a continuous research on adopted patterns and uh, really niche blogs. And here comes to play the Saga pattern. The Saga pattern is a pattern used specifically for this kind of use cases. So a multi-step transaction. So a transaction, so a flow that spans multiple services. And here is a really my kind our interpretation and how it fit into our use case. So imagine that we have this architecture, okay, pieces. So we have our orchestrator on the left, which has all of the API that goes directly to the clients. Okay, then we have a transaction center, which holds the database of the transactions, so their statuses, their creation date, etc., and also all the logic behind it. So all the flows, like generic flows that need to be created, and what service needs to go if someone has finished their work. And then we have the connectors. So basically from the orchestrators inside our system, all the different parts that communicates with the message broker that has been put into place and the other services. Here, the main part, of course, the backbone of everything is the event bus or a message broker that basically lets all these different services communicate between each other. So let's imagine we had received a call, okay, through the APIs. Let's start this transaction. Instantaneously, what we do, we start our transaction. So we store that we started a transaction somewhere, and we pick up from somewhere as well what is the flow. So what are the services and the steps to be done. And we send basically to start the first service. So the first service, the message service one start gets sent to the event bus, and connector, so the orchestrator subscribe also to all the events coming from the service one. Event bus then relies, or actually this message is being picked up by the service one APIs or connectors on its end. It does the job, perfect, success, wonderful. Then it sends the status update to the event bus that gets again picked up by the connector of the orchestrator that has been subscribed in the previous step. So once it receives these status updates, it simply updates the, let's say, the database or whatever this information is stored in the transaction center. So like, I don't know, service one started, okay, so service one succeed, perfect. Then the transaction center understands that the first step has been done and sends the second message, okay, the second message into the bus, which says, okay, start the second service procedure, perfect. And then again, subscribe to all the service to started updates. The event bus relies this message as well. And then if everything is okay, the transaction is actually completed. And this is actually pretty straightforward. We can also imagine this as a single, piece of code that does, okay, start, do this, then do that, and then return the results. It's quite straightforward, but we are forgetting that, of course, we are talking not in a single code base, but into a distributed system. So we have no, let's say, clear way of saying this and picturing it in all the paths. And by that, I mean, what happens if the service to failed? So what happened if the service to actually failed its goal? What happened then to the result of the service one? What happens in the Saga pattern is that, okay, let's imagine that this call, okay, the service to point start goes, the service to does something, but it fails. Then it says, okay, the event bus receives this failure status update, and the connector receives it and updates the database of the transaction. Perfect. But then in the Saga pattern, the transactions center is instructed to react to that, send back to the connectors that a rollback is needed from the first service. So the transaction center sends it back to the connectors, a rollback instruction, and subscribes to that again, to that service again. And then the service one can actually roll back its process from before. And of course, it will then update again the orchestrator to say, okay, I rolled back, everything is reverted, and update the transactions failed on step 2. So we can actually imagine it as a cascade kind of waterfall, okay, kind of effect. So if somebody on the chain fails its job, all the previous jobs have to roll back or recover from it automatically in a way that has been registered inside the transaction center. Okay, perfect. That's the theory around it. I hope I made myself clear and that's quite understandable. But how do we actually implement it? How do we implement it in our use case? This is our boxes lines around what happened. So we had a single GraphQL layer which held all the mutations and subscriptions to manage this stuff. And the front end was directly communicating to the GraphQL layer to then create new payment or transactions and receive asynchronously via subscription WebSocket subscriptions on the other side. So on the front end would create the payment. That would mean a fire and forget, um, a fire and forget action. Okay, so you would create the payment. It's like creating a flow. You would send it, and then you would have an ID as a return response for checking the status on. So you would subscribe to that transaction ID. After that, we would then the transaction is being created into the payment gateway. The payment gateway then has some kind of information. Like in our case, it was deployed on AWS, so we use DynamoDB to store all these transactional informations, and we store them there, the status, so the information, what kind of flow, etc. Then we from there we use DynamoDB streams to operate these different lambdas, okay, different piece of code that would start the step. So starting a step means getting a message on the event bus and sending it. That's it. And then also another function to roll back. So in case of some failure, we needed to roll back the different steps needed to be rolled back. So up to that point, basically. And of course, another function needed was to, at every point in time, whenever anything happens to a transaction, update its status on the table. So it reached this point, for example, this step, the inventory service step, but it failed. Okay, then report it to this update in the transaction would then be reported to the front end through the subscription. On the other side, so let's say on the bottom right side, which is on the event bus, this message was then relied to the inventory service, which was internal, and our third-party services. So in this case, we built some small connectors to receive information events from the event bus to send to our third-party CRM service and to Stripe. And of course, the main requirements around that is that they need to have APIs or tools to roll back certain kind of actions, which luckily for us, it happens so. So actually, how this solves the problem? It's actually pretty straightforward, but I wanted to point it out, a few key takeaways from this. First of all, it enabled us to have a clear interaction between independent services, okay, that we didn't have much control over. It also gracefully handles error in a really delicate system and use case. We want to make sure that no person, no customers lose its money or anything like that. So we wanted to have a reliable system underneath us. And it can be easily extended also because you could have like spun up different flows, different steps, and it doesn't take much to create a new step specification inside the orchestrator to support other external services. And of course, this means that we don't care as a payment gateway to care how these steps, so the payments, the inventory and stuff, and all this kind of stuff, how these kind of steps are done. So the payment gateway relies the payment gateway only concerns of payments. That's it. And of course, this has the nice consequence that the client could be almost real time, let's say, updated on all the different status changes. the client being the front end, or even DevOps team and other stuff like dashboard for observabilities and logs, etc. But of course, as I said at the start of this presentation, there is no silver bullet. There is no cure-all medicine. There is no magic uh, pixie dust, okay, around this. Also, this has some issues. Of course, the first one is the infrastructure behind it is complicated. You can see there are many pieces they need to be carefully placed in order. They need to be maintained, monitored, and all bells and whistles basically. And there was the need actually for a team to be formed around it, so the payment team, which was formed on that way. Another one is what happens if one of the rollbacks, okay, the reverts actually fails. We can't, it's like, it's like a dog, snake eating its own tail. We are back at the same problem. We can have an infinite loop of retries and stuff. We could, but there are also other kind of solutions. For example, we implemented a sort of dead letter queues for this kind of issues. And also, as I say, the complexity basically was into the communication and how we made all those spare, like, all those parts communicate between each other through our message broker. This in and I want to also add that usually this approach, it might be a good solution for us, actually help reduce all the manual handling of those issues or errors that were happening and failures, uh, so that in a 6 month, in the 6 month that it was put in place, not that was built in 6 months, but during the first 6 months of this, we only received one issue coming from the payment gateway by itself. I said, just giving out there a small metric around this. And basically, as I said, it's not that it's this solution is a silver bullet. Probably, if this is your case, will not or will actually solve your problems. But that was the whole point of the presentation, just to put up this real life example. And thank you for the attention. Yeah, and that's it. If you have any question, please. Mm, mm, mm. So, okay, I can see. Sorry, I can see the question. So, how to avoid latency in microservices? Okay. Uh, so, latency in micro. So that's another key point. Let's say, pain point. Okay, of microservices, because microservices, of course, are distributed systems. Okay, so it's let's say, um, it's almost a given that they come with a sort of latency in the different parts. Okay, which means that in order to reduce the latency between them, there are some ways, such as embracing this kind of latency, first of all, because there will be always some kind of latency between one piece and another, which are not on the same system. Another thing is, for example, to place, let's say, the more coupled microservices all together or kind of closer together. So, for example, usually when we divide, for example, different AWS accounts for different teams, which means all the microservices were communicating more with each other, were more closely together, and they didn't need any kind of extra accounts permission or going through the internet and stuff like that. Uh, yeah, some common practices to avoid latency. This could be one, trying to not rely. Probably one is to not to rely too much on um, only external ways of communicating. So, for example, if you're building on an AWS cloud project, usually you would not expose internal service API to communicate within each other. You would find another way. For example, make an example. Instead of calling an HTTP endpoint to call a Lambda somewhere, you would directly call it if it is in the same namespace or in the same area. It really depends how to avoid latency and this kind of stuff. It really depends on the project and the current infrastructure that you have in place. Then, what was the most difficult failure you had to deal with? So, if you're talking about this project in particular, okay, so handling payments and stuff, one thing um, was of course the whole error thing. So this project didn't finish didn't start as I presented to you. To get to this point of complexity, we run through several iterations. Bear in mind, the first version was one being handled by step functions and stuff like that. Um, uh, so the one of the biggest let's say difficulties that came with this project was to actually recover and how to recover and how to manage different steps. So how do we orchestrate in our payment gateway this stuff, and even how do we make the external services, so the CRM service as I showed, and the other one, the Stripe one, communicate with Even Bus. Have you ever had a situation where the Even Bus failed in production? Okay, failed in production. So let me remember, because from the time I was working there, uh, um, I can't recall a time where it actually failed. Of course, because when deciding and trying to put up this architecture, we would, choose the most reliable and with the one with the highest availability services to do that. For example, since we were in a AWS kind of context, we we relied on different AWS services to do that, and one of that is of course the Event Bus. Uh, so I have to say, it never had a situation where exactly the Event Bus failed in production, or even in our development environment, for example. What's a failing client? Well, I don't think it quite covers the topic of the presentation, but I think I don't know actually how to answer this question really. I have to say it. Maybe you're referring to the Fein REST client, one from Spring Boot. And if yes, well, those are easier way to basically write HTTP clients on Java Spring. And yeah, by the way, one thing that I remind myself is by adopting this, you of course create, so adopting the event bus as message broker of all the transactional information, usually usually so not usually, you create one point of failure there, but you have also way to get around it. Mm. So can see. Well, what is the expected for the? Oh, sorry. What was the expected? Oh, sorry. Yeah. So, what was the expected SLA for the presented system? Well, since it was so the company I was working with and the teams that were working in it were building the stuff for themselves. So there were actually like tech clients to report to about agreements or availability levels that the system need to be up. But of course, it was into our own interests to make it as much as available as possible, and we built in a way, so we relied on many cloud services, AWS cloud services to do that. We built in a way to move all the availability, okay, percentages out on the outside of the of the system. Okay, so we were most of the time, 99.99% of the time, let's say, it was failing because there was some error on the outside. So I don't know, the one of the services was down, or there was a failure in one of the call because some business logic was not working right, etc. But we built in a way that it was not failing on its own, let's say. uh Okay, so strangle design pattern. Is that a question, or is like uh, trying to let's say make a comparison with the Saga pattern? Because we are thinking that the Saga pattern in particular is a pattern to handle uh, transactions, okay, that span multiple services, so that they involve services that we don't have much control on. The strangle design pattern, if I remember correctly, from that is a way to transform kind of the system to a new or a old one. So probably microservice monolith one to microservices one, and they can easily coexist, basically because they serve two different purposes. Okay, the strangler, just to be clear, the strangler design pattern is basically the one, if I remember correctly, again, to create a single facade, okay, common entry point, that where the old system would, so the old system services, okay, the monolith services would refer to for doing calls, etc. For example, imagine that you have an old backend, okay, and you want to move to a microservices one. So, for example, you put up, I don't know, a GraphQL layer, okay, between the front end and the old system, and you basically start dividing, you start removing features, like replicating features and endpoints or services on the outside of it, and start, since you have control on this layer that receives all the calls, you can quickly, and once you're ready, shift the traffic to the different microservices, so that basically the old system gets a little by little depleted by all the requests and stuff, and then there is a point that where you totally replace the old system, that you basically shut it down and only use the new the new architecture or the new microservices basically. And it's making a comparison between the two is like, kind of compare apples and oranges, because as I say, they serve to different purposes, so to different goal. And in particular, kind of strangle pattern were used in the previous company, because we were moving from an old system that was a monolithic system, monolith sorry so we needed to scrape away all the features and create different and small independent system, so services from there. So another question: how do you support rollback in microservice? What if a microservice made a request to another microservice in scope of a transaction and received the rollback command after it? Could you give an example? So how do you support rollback in microservice? Okay, so first of all, I'd like to define what's kind of a rollback. Okay, so it's quite intuitive. So you make an action, a rollback is something that void or nullify, okay, the previous action. And the point of having this kind of pattern, if you don't, is to kind of not being in control of the single steps, okay, but being in control of the overall steps. So if you have a microservice, okay, that calls another microservice, etc., you probably wouldn't put the second microservices behind the first one, okay. You probably want to include it into the full flow to have it exposed, okay, to the full rollback mechanism, etc. So if your microservice, so if you have this orchestrator, okay, and you have the microservice being called from the orchestrator only needs to know and care about, okay, what is the if the job step failed or not, and then if it failed, do another thing to recover from it, or start the waterfall rollback basically. This is like a snowball effect that need to roll back everything basically. And so if you have this case, probably if you have control over it, probably you would try to move the second microservices call, okay, before everything, so that the let's say the first microservice has all the necessary information, or if all the necessary action has been taken before it. I hope this actually answered the questions, or if this is enough of a clear example. So yeah.
Hi, Francesco. Are
Hello.
you done with the session? I just joined to help Dwayne. Has some technical issues, so I can see where you are and if there's any questions, so that we can finalize this session.
Sure. Yeah, I was just going through some question,
Some
kind of
questions. Yeah.
discussions and answered. Yeah.
Yeah, I see that you had a great presentation. Thank you for being our guest in
Thank you, Andre.
Lunch and Learn. So I would just say for everyone, we are at the end of this session, and thank you, Francesco, for your presentation. Unfortunately,
Thank you.
Dwayne had some technical issue. That's why I came here for a rescue and see where we are. And but thank you again for everyone joining. You see these social links from Francesco. So if you have any questions, please, reach back to him and ask the rest of the questions. And I believe he shared most of the material already. But is there any final words that Francesco you want to say before we finalize session?
Well, not that are like impactful, like stay hungry, stay foolish, but please, yes, as I said, reach out to me if you have any questions or any outstanding stuff. I can even share with you the presentations deck if you want, no problem.
All
And I
right.
was really happy to present here today.
Great. Thank you. Thank you everyone for joining. Thank you, Francisco, for a session. Take care. See you guys. Bye.